Recording for part 2 here now. All right, so just keep the focus for a little while again. Here's a slight bit more complex for this little part, but it's the mathematics is really add maths. The equations just look a little bit long because they're written out that way, right? So just keep the focus and ask and stop me at any time if it's not making sense. So everything that we did before is all well and good, and we could handle any system with any number of simple poles and simple zeros. The simple zeros, in any case, if you're given any transfer function, and on top you have s plus 0, 1, s plus 0, 2, s plus 0, 3, and on the bottom you have s plus pole 1, s plus pole 2, s plus pole 3, and you put a gain here, right? Any number of these things, the approach to it, once you could get it in this form, is exactly the same. This, when you convert it, this k is going to give me a horizontal line at 20 log k. All of the zeros you convert, of course, you're going to have to convert it to the standard form. So all of these are going to be converted into a 1 plus j omega over z1, 1 plus j omega over z2, and so on. And all of the poles are going to be converted into 1 over 1 plus j omega over p1, right? Plus a 1 plus j omega, 1 over 1 plus j omega over p2, and so on. And you can draw them one line at a time. The 20 log k is a horizontal line at 20, whatever that is, a number. The zeros, all of the break frequencies, so you're going to plot z1, z2, z3, z4, right? This is all the z1, z2, etc., etc. You're going to have to plot the p1, p2, p3, p4, right, etc. All of the zeros are going to go to their respective, each one is going to go to its respective corner frequency and increase at 20. So you keep all of them nice and parallel, right? And then all of the poles are going to go to their particular frequency and decrease at 20. And you add up all the lines. The 20 log k, of course, is there. 20 log k going to be some line around here. So for between each zone, so you look between naught and z1, in this case, between z1 and p1, between p1 and z2, and so you go, and you just add up all and just draw a straight line between each segment, and there's your straight line response. Okay, so it's very easy and straightforward once you're able to get the system factorized into a set of simple poles. The little complexity comes when the poles are not simple. So the complexity comes with literally complex poles. So remember this when we were talking, and this has come up time and again. A general form for a transfer function, a second order transfer function that we have here on the screen, right? And of course, zeta, we know zeta is the damping factor, and depending on what it is, the transfer function is stable or unstable, and it might oscillate, or it might have overshoot, or it might have critical damping and the like. To convert this to the frequency domain, we make the substitution s equal to j omega, right? Omega naught is a constant, so that's not going to change. So when I substitute s equal to j omega, I have a omega naught squared. I have the minus omega squared below because it's j omega all squared. And then I have the 2j omega zeta and the omega 0 part. So this part here now, this bit here is a complex thing. We have a real and we have some imaginary components inside of there already. So how do we deal with that? Well, we rearrange the equation, of course, a little bit to try to get us into this standard form, right? So we divide through by the omega 0 bit, and the standard form now looks like what I have on the screen here. It's a complex number, so I want to plot the magnitude and the phase. So the magnitude, and perhaps more correctly, I should say the magnitude of that is a complex number, so it's 1 over the square root of a squared if it's 1 over 1 plus a plus jb, right? So a squared and b squared. So you square up the two of them and you find the square root. So, okay, it's a little bit long, but nothing too complex inside of here. But let's see what happens as the frequency varies, as we've done before. When omega is much less than omega 0, in other words, as the frequency goes to 0, these two components drop out, and basically what we have, remember, when you convert this to logs, it's going to be log of this minus a whole log of this. As omega goes to 0, this bit will drop off, so we just basically going to remain with a 20 log a. When omega gets very big, right, so as the frequency gets very high, notice what we have here. We have two bits here. This here is going to give me, right, an omega as omega gets very big, right? Remember, we have a square root of a squared here, so this is going to give me an omega squared below. This is just going to give me an omega over omega 0. So as the frequency gets very big, the part with the omega over omega 0 squared, this bit here is going to dominate the value of that. Fair enough? Because one part is squared, the other part is not. And when you convert the squared to the decibels, you're going to get that this is going to now, omega 20 log of this squared is 2 by 20 log of omega over omega 0, which is something that is going to decrease at minus 40 per decibel per decade. And we know that already. A second order transfer function will decrease at minus 40 per decade. So if I plot the straight line for this, I know that once at omega much less than omega 0, the plot is a straight line at 20 log a. When omega is much greater than omega 0, it's decreasing at minus 40 dB per decade because it's a second order transfer function. If it was a simple second order transfer function, then we could draw the two lines here, and that is our asymptotic plot right there. But the problem is that this one has a complex pole. It's not a simple pole, and it has a little factor inside of there, which is zeta, the damping factor. So we need to see what happens to that transfer function at this point here at omega equal to omega 0 as we vary zeta. Everybody following me so far? Everything behaves like a second order transfer function once omega is much less than the corner frequency, or omega is much greater than the corner frequency. So let's see what happens at the corner frequency. The normal thing that we did is that, remember, for the simple first order poles and so on, that the corner frequency just simply did this. The real thing would have done that. And we had a 3 dB error at that point in time. This case now, we need to see what happens as we vary the frequency with this thing at that point. Now this equation here, let's look at h of j omega. H of j omega, remember this is really, right? The magnitude of h of j omega is given by this function. Now this function, it's a quadratic that we're dealing with, a square root of a square. And this will have a maximum value when this bit here is a minimum. Fair enough? Normal maths. I have a over some value k. So a over k is a maximum when k is a minimum. So let's call this entire thing below here d of omega. So d of omega is everything under the square root here. You could forget the square root for the time being. So when this is the smallest value it could get, then h of j omega will be the biggest value it will become. Yeah? Nothing so complex. So I do some add maths now. How do I find the minimum of a function? Well, you remember how to do that. If I gave you a curve and ask you to find the minimum, you did the derivative and then you see what value would make the derivative equal to what? The minimum value of the rate of change would be when the derivative is equal to 0. Right? So I just make, and there's add maths we're doing now. So you call that bit under the square root, we're calling that d. H is a maximum when d is a minimum. When is d a minimum? D is a minimum when the derivative of d is equal to 0. So what is the derivative of d? Well, you could watch it through there and you could follow. Always double check what I have, because sometimes when I go from paper to formulae and typing the equation in, I may make a mistake. It happens and you've seen it. Like today, for instance, in the class, sometimes you copy things incorrectly. So double check. But let's assume for the time being that the derivative of d is this character here. And this is a minimum for some value where we have to solve what value of omega makes that equal to 0. So if you do that inside of here, you get a value of omega that makes that 0, and you could check that, right? Notice that the answer for omega that makes that 0 is going to be a function of omega naught and zeta, presumably. So if you look at that, when you do it, when you solve it, you're going to get that omega, the value of omega that makes this a minimum is omega 0, and there's a little factor there, 1 minus 2 zeta squared. Make sense? I'm not doing anything to Einsteinian here, right? Just hard maths. Yeah, no, maybe. Give me some feedback. Let me know if at least you're following me. Just hold the energy for a little while again. We're nearly there. Right? And you could replay it afterwards, but I want it, it's always important just to hear it, at least what I'm doing. Good. Perhaps it's better than no. So we get a value for omega, and I'm going to call this omega subscript r here equal to omega 0 by a little factor inside of here, 1 minus 2 zeta squared. Now notice omega always has to have, is a frequency, so it must be a real number. Right? Omega r, in fact, must be a real number. We can have an imaginary value. So this can only have an imaginary value if zeta, 2 zeta squared, right, is less than 1. Otherwise, this whole thing will be a square root of a negative. So we have a constraint here now that zeta has to be between 0 and 0.707, 1 over root 2. Yeah? At that point, this the derivative of the denominator is its minimum, or sorry, the denominator is its minimum at this value of omega. Therefore, h j omega peaks or gets its maximum at that value, and that's why we call it the omega r. It's a resonant value, so it's going to peak at this value, and it is only valid, sorry, if zeta is within this range. So when you go back to the second order equation that we had, remember originally when we discussed it before, we said that zeta, first off, zeta had to be positive. We said that, and we had a constraint with zeta between 0 and 1. The closer to 0 that zeta went was the more the step response oscillated. The closer it went to 1 was the more that the response was damped out. In terms of the frequency response, so we're seeing that zeta is further constrained to actually be between 0 and 0.707, 1 over root 2 now. Yeah? And normally, because zeta is fairly small, zeta is fractional, right? It's between 0 and 0.707. So zeta squared is usually a bit less than, even 2 zeta squared is normally a bit less than 1. So when you take the difference and you find the square root, what you find is that omega r, for most intents and purposes, is fairly close to omega 0. So when you plot it on a log graph, for instance, it's very difficult to distinguish between, let's say if you calculated an omega 0 was 100, and omega r turns out to be 105 or 96. There's no way on a log plot you're going to be able to get that close to 100 to distinguish a 95 or a 105 kind of thing. So we normally, and it's understood, that omega r is approximately equal to omega 0. Yeah? So straight off from the equation, you could kind of find that out without doing this. And what happens now is that if you put the magnitude of the transfer function now, what is the behavior of the transfer function at omega equal to omega r? So if I go back a couple of slides here, right? If I put omega equal to omega r inside of here and juggle it around a little bit, I'm going to get that the magnitude of the transfer function looks something like this. Right? So by substituting omega equal to omega r and this relationship here that we just derived, a little bit of algebra, and you could try it, right? So you take omega r is this. So omega over omega r, if you go back to the transfer function here, right? Omega over omega naught, or omega r over omega naught, right? Omega r over omega naught will be this fact, 1 minus, sorry, the square root of 1 minus 2 zeta squared. So I could go back to the equation and substitute for omega over omega naught, sorry, not that equation, this one. I could substitute for omega over omega naught in this thing here. And then if I come back and I plug it in and I call that at omega equal to omega naught, the magnitude of the response at resonance, it actually now comes back down at the resonant frequency to just being totally dependent on zeta. Yeah? And of course, if you require it in decibels, then you take the 20 log of that. And when you plot it, this is what happens. Remember, we had, for omega less than omega 0 is a nice straight line. For omega much greater than omega 0, it's a second order function, so it's decreasing at minus 20 dB per decade. Inside of here now, at the corner frequency where omega equal to omega 0, right? And as I said, if you plot it on the graph, omega 0 is very approximately equal to omega r. You can't tell the difference at that point. What is going to happen now, depending on the value of zeta, because this, the magnitude of the response at that point depends now on zeta. So look at this. When zeta is very small, this magnitude is going to be high. And when zeta approaches the 0.707, then it minimizes itself, right? So that at that point, if you were to plot it, you're going to get something looking like this, right? Let me just zoom that a little bit. Right? So look at the values of it. When zeta is 0.7, which is, remember, that was a constraint, 0.707, you get a nice, smooth second order response here. Right? This is minus 40 and this is flat. When zeta is 0.1, for instance, look at what happens at the point. It goes here and the response does this. When it's 0.01, remember that's a damping for the system, you get this sort of response. It does this and then it gives you a very sharp peak at the resonant frequency. This is MR. Right? So you can look back and so you can now look at, for instance, if I were to give you a response like that, you could look at this and you could go back to the little bit of math here. And from this, you could tell me what the damping of that system is, again, from the frequency response. Make sense? Yeah? No? Maybe? Right? It's very straightforward. You just have to read it again. And what I suggest is that when you're reviewing the thing, don't wait too long to go over it. Right? So it doesn't sound like it's Greek or something totally new again. So what about a phase? Remember, we always have these two things. So this phase, the argument of j omega, remember, we have if you go back, let me just go back to the equation here. This is the magnitude of j omega here. Right, I have to keep putting the little line here. So this is the magnitude of j omega. The phase of j omega is really the phase of this, which is a constant. So that is, if it's a positive constant, it's 0. If it's a negative constant, it's minus 180. So the whole phase of this thing depends on the behavior of this part of the equation. Right? So just like we did before when we were talking about the simple poles, the argument of that bit now depends on the relationship of omega and omega 0. When omega is as omega approaches 0 or it gets close to 0, this is 0. When omega gets very large, right, as omega gets very large, this now goes to minus 180. And at the point when omega is equal to omega 0, then we're going to have a 1 over 1 basically. Sorry, a 1 over 0, which is minus infinity. Or infinity, 1 over 0 is infinity, but is minus the tan of that, which is minus 90. So that the plot basically starts from 0 and it transitions to minus 180. We expected this because it's a second order, right? Remember, a first order pole, the phase goes to minus 90. A second order pole goes to minus 180. A third order pole goes to minus 270. So this is a second order pole. So at some point in time, it's going to transition to minus 90. But at omega equal to omega 0, it passes through the minus 90 point on its way to minus 180. So in other words, the phase plot does this. And of course, how the dotted line, which is the real performance, behaves changes significantly with zeta. So on the same diagram, you can see that when zeta is very small, when zeta is very small, and let me just zoom it up a little bit again. When zeta is very small, the turquoise line here, it changes very suddenly from 0 to minus 180. Right? But when zeta is large, like 0.7 here, we have the red line, right, which is a gradual change from one phase to the other. So the point with this is that, right, if we go right back to, we don't have it here, where were we? Yeah, okay. If we're dealing with a system that has simple poles and simple zeros, then it's just a question of the simple zeros increase at plus 20, the simple zeros decrease, sorry, the simple poles decrease at minus 20. Zeros increase at plus 20 dB, poles decrease at minus 20 dB per decade. A real second order pole decreases at minus 40. A real third order pole, if that ever came necessary, would decrease at minus 60. A complex second order pole, which is what we just did, decreases at minus 40 as expected, but here at the transition from the 0 dB line to the minus 40 dB line, here is going to have a change in amplitude that depends drastically on the damping of the system. Once it has complex poles, it will have a damping factor. Once it has a damping factor, if the damping factor, first of all, the damping factor has to be between 0 and 0.7. And then once it is between 0 and 0.7, then the closer it is to 0, the higher this peak in the response is going to be. So it's going to do that, and for a very small damping factor, it may do that as well. Now, that is incredibly important from a practical point of view. So if you're designing something, for instance, as we spoke about it, like a hearing aid for someone, and the hearing aid, you're putting a low-pass filter on the hearing aid to get rid of high-frequency noises that may be interrupting the person's hearing. And you put in a second order that somewhere inside of there, the transfer function of the filter is second order, but the poles are complex. If you're not careful, then at the cutoff frequency, you're going to be getting an amplification of the frequency at that point in time. And look at this case. If you look at the axis that I have here, it's flat at 0, which means no gain. But all of a sudden, you have a gain, in this case, a maximum gain of 40 dB. Right? So 20 log of whatever the thing is 40. Log of the number is 2. Right? So what's the inverse log of 2? 10 squared, which is 100, right? In other words, from a pure practical point of view, something like this means that it's going so, but as you approach the cutoff frequency, the gain goes up by 100. So imagine that you have this thing in your ear, and at what is supposed to be the cutoff frequency for whatever this filter is, just before it cuts off and starts to roll off, it is going to amplify by a factor of 100 whatever that particular frequency is. Right? So as somebody pointed out in the class this morning, you're going to hear a very loud screech every time the frequency approaches that point. And that is, of course, as for somebody with hearing impairment, that's an absolute disaster. All right? When you're doing your control systems next semester, you're going to see situations like this that will happen in other types of control systems, process control systems, and temperature control systems as well. And you have to be aware of that, and you will have to do something, for instance, to decrease the damping. But the damping notice what happens here. The small damping is giving me a peak in the response here, right? But the small damping factor is what gives me a sharp, well, it ties back into the time response as to whether I get oscillations or not as well, right? So you have everything sort of tied in together. In one case, you're going to get oscillations, and in the other case, you're going to get a peak in the frequency response. So you can see where the two things connected, all right? So we looked at it from both aspects, from the time domain, which gave us that particular issue with the damping and what happens to the response at that point in time, and from the frequency domain, as you see when you draw the frequency now, that you get an amplification of the frequency at the cutoff. Yeah? And of course, here's one for you to try and see and sketch. Remember, this is all freehand sketching here. So how you would sketch something like this, right? If you were to draw it as a practical thing, what you would do is that you're given the transfer function. The first thing, you get the transfer function, you get omega r, right? 2, you get the damping factor, right? Or the other way around, you get omega r, then you get a damping factor. Then from that, you get the magnitude of the response at omega r. So what you do with the straight line Bode plot would therefore be, you draw the straight line here at up to omega r, you draw the other line decreasing at minus 40 because it's a second order system, and then you draw a simple straight line here. You draw a straight line here and indicate on the straight line that the magnitude of the response at this point is 40 dB. Right, so somebody watching the plot, the straight line plot, will see, okay, it's a second order system and it has a rise in the magnitude response of 40 dB at the resonant frequency. And from there, they can calculate everything on this diagram. You can calculate now. Right, you could go back and get a transfer function. So you will see, and there's some questions like that you will see when we're doing the, if you do the past paper questions, or you have started to look at any of them as yet, right? You will see there were situations where I gave you the response and told you, okay, this is the response. Of course, I gave you the phase response. This is the frequency response to suggest a second order transfer function that will give me that sort of behavior. To do that, that means you basically have to determine zeta, mr, omega r, and then you go back to the equation that we started with, right? Which is this one here, right? So you're calculating, you're basically looking at the thing to calculate this and calculate that and calculate that. So they could just plug in the values inside of here and tell me from the Bode plot, right? Given the Bode plot, given the particular type of frequency response, you should be able to tell me what sort of transfer function that is. And of course, you always watch and make sure that everything is in decibels and in log scales, okay? Fair enough? So I'm sure you have questions as you go through this. You're going to have to think about it. You're going to have to read it carefully. The other problem sets I think are available, so you could probably start going through them. If not, I'll activate all of them because we're doing enough now that you could kind of go through and pick and choose the problems as well, right? But you're going to listen again to this or just read this slide and try and follow it through. Listen to the parts that you're not clear about, and then come back to me with questions. All right? So that now will conclude our topic discussion on the Fourier series, Fourier transform, frequency response, and Bode plot lecture parts. Most of the Fourier series stuff, of course, you did the more mathematical part of it in ECNG 2013. Our interest here was how to use it. So given a transfer function, how do I get how it behaves in frequency, right? We also use the Fourier transform to be able to solve some differential equations where you didn't have initial conditions. For instance, when you're dealing with non-causal situations as well. and then using the behavior of that to allow us to draw some straight line frequency plots, asymptotic plots that give us an estimate of what the real thing looks like without having to do the real calculation itself. Yeah. So the other two topics that we have to accomplish, well, we have the Z transform now, which is the last major topic, and we have some lectures on stability, right? I'll probably do, those are very straightforward. It's a very nice, almost a mechanical way of assessing stability. So I'll probably do those as recordings to post for you to listen to. And we will start our discussion on the Z transform now, coming up next. The Z transform is the more unique one, is the one that we haven't had a look at, or any sort of relationship with the Laplace and the Fourier transform as yet, right? It's a little bit different. It's all discrete time system work. So we're going to delve into that, and that's a last major topic. And the small topic is on some stability, a stability assessment method, which we will do. Most of it will be done by, I'll give you some, I'll record the lecture for that. And you could listen to that, and then we'll come back and discuss it when we look at problems. But that one is very straightforward to deal with. Yeah? Okay, so thank you very much for your attention. Again, it's been a long day, and we covered a lot both in the morning class and this afternoon today. So we have quite a bit of stuff to mull over and concentrate on. And of course, when you do that, then you'll be able to see if there are some things that are not clear at all. I will take the same approach that I took telling you for the other class. So we'll compile a sort of list of the main things that might be giving people some issues. And also I will see for myself from the midterm as I correct them going through, where people might have been misunderstanding things if it turns up there. And we will try and make some time to focus on that as well. Yeah?